Okay, so welcome everyone. Good afternoon, everyone. I'm Pietro Manzoni from Polytechnic University of Valencia, and welcome to this talk which is related to the series of Connect Them All. First of all, we have to say thanks and welcome Roberto Morabito. Thanks, Roberto,
Thanks, Pietro. Thanks to you for the invitation.
And so, brief introduction. Roberto Morabito is an assistant professor in the Communication System Department at Eurecom, France. Before joining Eurecom, he was a senior researcher at the Department of Computer Science of University of Helsinki, and before he was part of Ericsson Research Finland. His work is at the intersection of IoT, edge computing, and distributed AI, focusing on trade-off in AI service provisioning and orchestration under computing and networking resource constraints. So today's talk would be From Edge to Extreme Edge, exploring the dimensions of AI inference in IoT. I'm sure it will be a really interesting talk. If anyone attending on the YouTube channel wants to ask a question, please write it down in the chat channel. And when I see the right moment, I will ask the question for you to Roberto.
Sure.
So please, Roberto, whenever you're ready.
Yes. Thank you so much. Thanks so much, Pietro, for the opportunity and for inviting me to the seminar. And I've been actually following a few of the seminars, and pretty much, I think all of them. And perhaps today's presentation might be a little bit different in terms of the fact that it's a little bit more application agnostic compared to what we have. I had the chance to see in previous talk, but I hope to kind of bring something to the table in this seminar. And as I mentioned, the idea would be to actually go through a different topic that I've been kind of shaping my research in the last few years. So we go in the context of this dimension of AI inference at the edge and IoT. Pretty much the idea would be to go through three different main areas. Let's see, you can see also in gray one part. Let's see if there will be enough time also for discussing the third item. But pretty much I will start with the work that I've been doing first in what we could define nowadays edge computing and edge AI, and then a little bit in parallel, but also somehow overlapping and in parallel then some of the work that from the edge has kind of moved to something a little bit more constrained in terms of device capabilities. So what we usually call tiny machine learning and related. And then also, if there will be enough time, I would like to discuss a little bit also new possible ideas or perspective of what it comes next. Of course, there is a big hype with generative AI, and a little bit I would like to discuss whether there is an opportunity for also for edge and IoT given the context. Thank you so much for the introduction. Of course, this is a range of work that is kind of spanning in the last few years of my research. So something that I've been starting during my postdoc in US, and then in parallel continued during my tenure at Ericsson Research, and then continue at the University of Helsinki, and nowadays at Eurecom. And a little bit for setting the stage, respect what we are going to talk today. It's important for me to also define and trying to provide a definition about what we can consider an IoT device. Of course, we can find online many definitions, but it's important to kind of bring in this sort of definition, because I would like that also it will make somehow clearer what are the distinction between what we are going to see at the edge and in the tiny machine learning space, of course, for what concern AI inference. And in this respect, I would like to bring up this definition that is actually defined in the context of ITF, of the Internet Engineering Task Force, where there is a sort of internet draft in which we sort of define the different terminology for constrained network and constrained devices. And I would like to kind of snapshot this sort of differentiation between what we can consider extreme edge and edge computing. You can see that from the left-hand side and right-hand side that there are substantial differences in terms of capabilities for this type of devices, especially in terms of memory, the possibility of processing the certain amount of code size, for example. So let's try to bring in this definition and this distinction between extreme edge and edge devices, because somehow will be also useful in the remainder of the presentation. And as I mentioned earlier in the first part of my talk, I would like to discuss a little bit from my research activities in the context of edge and edge AI. And my background is actually in telecommunication engineer, but my PhD is in networking technology. Although I've been working during my doctoral studies quite a lot in IoT and edge computing, especially for what concerned service orchestration, service provisioning in a wide range of application. And when I start to look, trying to be inspired for new areas to investigate in my research, I was somehow triggered by the fact that when we look at this type of devices, there were interesting forecasts with respect to the fact that it was somehow given for granted that the amount of smartphone or also tablet devices would have increased, the pervasiveness of such devices for example, in the 2020, from 2020 to 2024. But what's interesting for me to see is that also the kind of the increased factor for the enterprise edge, this type of a specialized edge equipment was actually increasing at a much faster pace, at least in the forecast, and then the forecast was actually confirmed. When we think about this sort of enterprise edge devices, I'm referring in particular to devices that nowadays can embed a sort of AI capabilities. So classic example could be Jetson Nano devices like from NVIDIA. We have a wide range of devices, but for me it was interesting to look at these devices from also heterogeneity point of view, the capabilities that this different AI accelerator could actually bring in a much more complex system. So I start to look a little bit at different AI accelerator like TPU from Google, VPU from Intel, and start to think a little bit on what kind of research could have been done in that particular area. And just interesting, I would like to mention here that when I was preparing the presentation, I was also looking a little bit at the background and the history of what I've done in this context, the related literature, and I found one of the most inspiring paper about the study of AI inference at Facebook, specifically on device inference. And as you can see from the left-hand side of the screen, at the time, the sort of capabilities of the device were rather limited. There were, of course, already quite good performance from the inference per second point of view, but everything was pretty much running on the CPU. There wasn't, at least not so in pervasive way, the possibility of relying on this sort of AI accelerator, and the performance were good, but not exceptional compared to what we can have today. And an example is for the last smartphone, like this Galaxy S24, which can run extremely complex generative AI workload, and of course, like those type of performance are now much higher, and we have the possibility in this type of devices to process a very complex application. So the hardware was somehow one first first kind of way for me to be inspired about the new possibility in this specific area. But then there were additional aspects that I wanted to take in consideration. When I was looking, for example, at the related literature and the practical application, like the one I just mentioned, for example, from Facebook, they were pretty much following the same pattern with scenarios that were perhaps involving a single edge node or a single IoT end devices. So my idea was actually to trying to look at scenarios in which multiple edge nodes could possibly cooperate between each other. And the other aspect, which is somehow touching upon what I've been mentioning earlier, was the aspect of heterogeneity. There weren't many scenarios in which hardware heterogeneity and also the networking aspect, how, especially if we are considering distributed scenario, how the networking could possibly affect the provisioning of this sort of workload and application, which are also possibly time sensitive. So the idea was actually try to look at a more complex scenario where we could have multiple edge devices, multiple end devices, and those devices were not were of course given the opportunity to cooperate and to work in a single network distributed system with different AI capabilities, relying on those type of AI accelerators. Example of those AI accelerators that I was showing earlier. And the main question that I was trying to answer with this work is how can we ensure to in this sort of complex scenario, how can we ensure an optimal resource allocation for the execution of AI inference across multiple edge nodes, and when we need to serve different end devices. And in this respect, when we look at such complex scenario, the idea was to look also from a system perspective. At the time I was working at Ericsson, so there was also the interest to look at the distributed aspect of the system in its entirety. So obviously taking consideration the networking, but also the idea of having a system that would kind of break the silos that these different AI accelerator and this heterogeneity could possibly bring in. So the idea was to have this sort of plug-and-play interoperability between, as a requirement, plug-and-play interoperability among different devices embedding different AI accelerator, the opportunity to look at AI inference service provisioning in agnostic way. It doesn't really matter for me whether it's a TPU, GPU, or VPU, but for me as an end device in that sort of distributed scenario, I just care that my AI inference service can be delivered with a satisfactory performance. And obviously for trying to build such complex scenario, obviously there was a big requirement and in terms of orchestration capabilities. The idea of kind of combining this computing and networking aware orchestration mechanism for ensuring, for example, that the quality of service of an AI inference service could be satisfied. And just to give sort of adding something more in terms of requirement for this type of scenario, the idea, and here I always like to kind of refer to a vehicular scenario, so where or UAV or smart cities, where there is high level of heterogeneity, high level of dynamicity, also from the network perspective. And obviously, when we look at the provisioning of these AI inference services, we really can't forget about the fact that there is, of course, a computing requirement, the execution of the AI inference workload itself, but also there is a strong communication requirement. So we need to make sure that the actual latency, the network latency doesn't really compromise the overall quality of service and experience. And additional requirements where obviously also in terms of reliability. My idea was to look at this sort of edge computing, especially from the constrained devices. I've been showing at the beginning of the presentation this sort of categorization, and the idea here was to look at edge devices that could possibly be considered to some extent constrained. So something comparable maximum at a single board computer like a Jetson Nano or Raspberry Pi, something similar like to those kind of devices, and far from server machine that are actually also used in multiple and several edge computing scenario. So in practice, coming back to those requirements, and we start to work and define the scenarios, trying to define and think how we could try to tackle the research question I was mentioning earlier. And in particular, we start to focus on specific edge AI accelerator. And here just a summary of the 3 types of AI accelerator I was already mentioning earlier that were somehow making this heterogeneous and complex distributed network system. And you can see also that there is a certain degree of heterogeneity also from the not only from the AI acceleration point of view, where we have TPU, GPU, and VPU, but also from the memory perspective, also from the CPU perspective. And this is, of course, something that eventually impacts the provisioning of these type of services. One big implication of this sort of heterogeneity that we bring in this type of scenario is the fact that by default, these type of devices work with completely different software pipelines. For example, if I want to run my machine learning model on a Coral dev board, the board produced by Google, which takes advantage of a TPU, tensor processing unit, I need to kind of follow a specific pipeline and then kind of package the model in a way that this can be used only and exclusively by the underlying hardware. The same applies also for the other devices like the NVIDIA Jetson Nano or the Intel VPU. And obviously, when we look at this heterogeneity also from software perspective, there are 3 major implications. Still referring obviously to this sort of distributed scenario. The first one is that we really can't ensure a sort of device interoperability, let's say, out of the box. Interoperability among devices was one of the key requirements. If we rely on these devices, let's say, out of the box, we certainly can't have this seamless interaction between devices in just a plug-and-play fashion. Then the other strong implication is that because of these different pipelines that we use for compiling the AI model for kind of fitting these sort of constrained devices, also the AI inference latency processing might vary from board to board. And when looking at the whole scenario, distributed scenario, we are sort of lacking a seamless AI inference provisioning offloading. Again, the idea for us was, and obviously taking consideration these 3 implications all together, of course, create a scenario that is not so simple to be handled. For us, the main requirement was essentially trying to have this sort of agnostic network AI system where the AI inference in edge computing could be provisioned in a seamless way, regardless of the node that is executing it. And in order to sort of tackle this problem, we have envisioned a software platform architecture that trying to kind of tackle those big requirements that I was mentioning already earlier. The interoperability, having this sort of platform agnostic service discovery and provisioning within the Edge AI cluster, and obviously because of the constraint that we have in terms of computing and networking, seamless service orchestration when we are actually provisioning the devices. Provisioning the services within the Edge AI cluster. You can find the references later about like all the details of this architecture, but I would like very briefly mention about some of the main components. The first one relates to the AI model management. This was work originally done during my postdoc, and in comparison with some students there. The idea was to kind of in an automated way, if we, let's say, take an object detection model and we want to compile it and make it running in this type of boards in a seamless way, we have been automating this process of downloading the model, for example, from a model repository, converting the model and storing it in the dedicated hardware. So this was, of course, an important piece of the architecture. And then obviously, looking at the real-time provisioning of these AI inference services, the AI inference management with a bunch of different submodels was obviously playing a key role. And what I will try to do soon is essentially providing you a short demonstration for each of the main component of this solution. But just to recap, and before kind of getting into this demonstration, the scenario that we are trying to analyze here is an end device. It could be an extremely constrained device which is not capable of executing AI inference locally, and it's basically asking help to the edge. And when we need to take in consideration the node that will provide this AI inference service, the execution of this specific AI inference service, we need to take in consideration jointly the computational capabilities in real time of the edge devices, and also the network performance. Here you can see a very basic example of different network latency, different load for each of the devices. So it's a complex trying to understand where to allocate the provisioning of a specific service. Also because, especially from network latency perspective, and there's not really a one-size-fits-all rule, things are quite unpredictable. Network latency is it's very hard to predict. In this specific system, and you will find the details in the papers, we have been using some very simple time series forecasting that could run locally on each of the devices, in order to understand also between edge devices, let's say in a sort of inter-edge and intra-edge, what kind of capabilities the other nodes have, and in order to, when we offload the execution to another node, making sure that we offload the execution to an LT node. And essentially, the main question when trying to demonstrate this.
Yes. Sorry if I interrupt you, because I was thinking. So, do you make any? Maybe you are talking about it later, but are you making any kind of hypothesis about the connectivity, the technology that you are using to connect your end device to the first edge node that is available to do some edge computing? Are you assuming that there is some, minimum bandwidth? Because maybe I'm thinking IoT, so I'm thinking maybe technology like LoRaWAN, NB-IoT connecting. So are you making an assumption of the minimum requirement for connectivity?
So in this particular case, the type of workload that we were considering, since it was mostly, for example, object detection, so there weren't so many constraints in terms of bandwidth, but the main factor there was the latency. When it comes to the latency, the way we have modeled the latency was actually through a testbed. A 5G testbed was one of the first one that was developed at Purdue University. And there we have been through our testbed. I'm actually presenting the testbed in the next slide. We were modeling the scenario that the network latency based on the several logs and performance logs that we have been gathering at the time. 5G was actually at the beginning of the rollout, and that one was one of the first 5G testbed. But essentially, we weren't really considering constrained connectivity in this case because of the specific use case that we have been considering. We have actually another branch of work. Hopefully, I will get a chance to present that is the third item in the presentation about this hierarchical inference, in which the context of where we are actually running AI inference on the end device itself. So we suppose that we have the possibility of running AI on the device, and then the decision whether to offload or not to the edge, taking consideration also these bandwidth and energy requirements of the devices.
Okay, thanks.
So yeah, I was mentioning that this was pretty much the testbed that we were defining and using in our work. As you can see, there was a high level of heterogeneity with all the three different accelerator that we were using. Introducing the heterogeneity, and also, of course, as I just mentioned, the emulation of this 5G network with data that were actually gathered in a real testbed. And just to show you a little bit how the different component of the three main requirements about the kind of the service discovery of these services, making sure that each of the nodes have enough capabilities for getting assigned the execution of an AI inference workload, and then the orchestration. I would like to show you a few very simple demonstration here. So in the first case, the inference service discovery was actually done in a very simple way. We decided to use a simple DNS-based inference discovery, and what you can see here is essentially the terminal of the end device. And in this particular case, the end device is kind of querying an object detection service, and because thanks to the infrastructure and software architecture that we have been building, the end device is able to understand first which kind of edge node in the cluster has available this object detection service, and I would like to remark here that we can see, for example, listed the edge 3, edge 4, and edge 5, and that doesn't mean that the object detection was actually available only in those nodes, but it could be that the edge, for example, the edge node 1 also would have available this object detection service, but in that particular moment it would be, for example, extremely overloaded, so there wouldn't be enough resources for kind of making space to the execution of an additional service. So to show you very briefly how this concept work, so you can see all the health checks, and you can find obviously all the details in the related publication. Here the end device is querying this object detection inference service, and it will get answer from the accelerator VPU, one of the node in the cluster. Now I was supposing that we are adding some stress in one of the node. This will trigger some L check that will kind of make that node not available to the rest of the devices. And this means that in the moment I'm going to ask again for the object detection service, as you can see again on the left-hand side. Now we will receive a kind of answer from an alternative node in the cluster. Obviously, behind there are like additional mechanism respect the network latency and the way in which we kind of set this healthiness of the node. But of course, there's not enough time for going to into the details. And what I would like to show you here is also an additional use case in more practical, where we have an application that, for example, that is running on the Coral board, and as soon as the node turns to be overloaded, the execution of the service will be seamlessly migrated to another node. I will show you briefly the demo. This was pretty much the user interface that we were building. There was, of course, for demo purposes, we were reducing this scenario to just 2 AGI nodes, but this was actually there was the possibility to see all the different nodes belonging to the cluster. And you can see that there is also kind of awareness of the network latency among all the different end devices and edge devices. I mentioned already that we were using a sort of time series forecasting, very simple in a way that this wouldn't impact the performance of the devices. It was very simple, a very simple algorithm that was kind of monitoring constantly in each single node the latency that we would have in the cluster respect each of the single end devices, and also the latency respect all the other edge nodes. So just to show you in practice how this would work, and again, here the idea would be to kind of take in consideration both the network latency and the computing execution of the service. So what is happening here, I stop 1 second the video, is the execution of object detection service on the in one of the devices, in this particular case on the Jetson Nano. And what we will see now is that as soon as the quality of service requirement will be kind of violated, there will be a seamless migration of the execution of the service in the other device, which is in this case the Coral TPU. So essentially, from the end device perspective, for me, it doesn't really care. I don't really care whether it's going to be a GPU or TPU. Of course, there are some implications from a performance perspective, and we have been studying also those. But the provisioning of the service is actually happening.
I have a question from more or less related to this one by Andreas.
Yeah.
It says, when talking about quality of service, how is the problem solved to provide the service with the max delay guarantee if the network connection is unreliable?
No, it's extremely complex. I mean, of course, like from the theoretical point of view, there might be some optimization, but in practice, the idea here would be to use a very simple way, greedy heuristic approaches, and the system was actually developed and deployed. So we were relying on greedy heuristic approaches and trying to cope with the capabilities of the network and the computing performance in real time. From the network, what we were doing is kind of monitoring the link respect to each end device and edge device in the last minute, 5 minutes, and 15 minutes. And then we were actually building this sort of exponential moving average with also specific factors that could be also adjusted based on the requirements of the application. If we would would like to mitigate the kind of a short-term fluctuation, we would set in a certain way. It really depends, let's say, on the history of the link. That was essentially our way to cope with the unpredictability of the network.
Okay, thanks.
So yeah, that's pretty much like wrapping up this first part of the presentation concerning the Edge AI. Just one additional note here is that I wanted to show that in this kind of Gartner forecast, technology forecast, it's interesting to see that all these related aspects of AI orchestration and automation are still still demand a lot of efforts from the research and development community, while the Edge AI, for example, is already kind of on hype, but there is still a lot of work because of the complexity of of such environment. And here you can find link sources, the work published in this context. You will find additional details, obviously also concerning all the details, the health checks, the management of the network, and so on and so forth. And now let's move on the second part of the presentation. And here the idea would be actually to move from the edge to tiny devices, even more constrained, kind of broadening the network computing spectrum. And I'd start to work in this area of TinyML almost in parallel to the same period that of the work that I just presented. And essentially, like here we are talking about a completely different scenario. We are sort of at the intersection between embedded system and machine learning. And when we compare from hardware perspective, the key differences between these sort of devices, we can see that the orders of magnitude, the difference is extremely complex. So obviously, all the kind of possible optimization and that we can have in these Edge AI devices with specific AI acceleration, actually we can't have the same in this particular context of more constrained devices. Just very briefly, if, for example, we look at the software perspective of tiny machine learning, we essentially, if we don't deal with such constraint, we suppose like we are running these AI services algorithms also on more capable devices. Nowadays, with all the Python or similar data science libraries, we have actually possibility of in a seamless way running almost the same code, unless there is we have seen some complexity at the edge. But if we think about the cloud development, we can almost run pretty much the same code from one hardware to another. This type of portability, when we compare microprocessor and microcontroller, actually is not guaranteed. This is, of course, like the trade-off that we have for bringing machine learning also in this type of devices. We have multiple advantages, obviously, in terms of cost, in terms of power consumption, but obviously the code portability in the context of microcontroller becomes a big challenge. And essentially, what we start to do few years back already was to trying to in a similar fashion as we did for the edge pure, let's say pure edge case, was trying to understand like how can we enable TinyML in a kind of sort of uniform way among different platform and increase the portability. Here we are talking about completely different level respect to what we have seen in the case of Edge AI. And we start this this work called TinyML as a service at Ericsson, and these were like the first kind of contribution in this area was end of 2019, so relatively early stage for TinyML, and the idea here was to kind of break this sort of wall between cloud and edge and embedded system. But also, now I will explain shortly what was the TinyML as a service about. The idea here was also to kind of bring us an additional IoT flavor to the whole scenario. Similarly, as I mentioned when talking about the kind of R&D effort in the context of edge computing and edge AI, also in the context of TinyML, of course, there was a lot of effort on the optimization of the single algorithms in order to fit in this extremely constrained control. But what we wanted to bring in was a different perspective. Also here, trying to consider a much more complex environment where perhaps also the networking aspect would play a key role. And we essentially came up with this idea of TinyML as a service where whether it's a cloud or edge, we wanted to build this abstraction layer, which would be also in this case agnostic, but taking in consideration the additional limitation that the constrained IoT bring in, and the extreme edge that we have seen at the beginning bring in this case. And here the process for TinyML was extremely simple. We were collecting the device specification, for example, CPU or MCU capabilities, memory, peripherals, and then based on the device information, trying to use the most suitable compiler, ML compiler, for being for compiling the model, and then let's say shipping it into the device. And the kind of the IoT flavor that I was mentioning earlier is that we since day one we decided to rely on a IoT protocol. Surely you're familiar with the OMA lightweight end-to-end protocol, which is basically building on top of CoAP. So for very constrained devices, the idea was to kind of taking advantage of this protocol in order to bring this IoT flavor and the possibility of relying on mechanisms that were already existing and implemented like software update, firmware update to this tiny machine learning world. So we wanted to kind of extend this embedded system machine learning intersection with the IoT network as well, and kind of defining the TinyML as a service. And in practice, and you can also then check later on the references, we were relying on three different what we called interfaces. One was the compiler plugin interface. It was a sort of midwell for kind of trying to fetch, like as I mentioned earlier, the device information needed for compiling the model for the most suitable platform. Then there was the orchestration protocol interface, relying on the capabilities of lightweight end-to-end for software firmware update, but also connectivity management. This was an extremely important aspect. Connects to one of the questions done earlier, trying to understand what also the connectivity status between the TinyML as a service platform and the device themselves. And then of course the most important one of the most important interface was actually the Inference model, which was the package, let's say, compiled and that could be shipped through the lightweight end-to-end and fit into the device itself. And also in this case, we have been working for developing towards actually this project. When who was driving this effort was actually already leaving Ericsson, and we have been using a bunch of different technologies for having a very simple proof of concept of this TinyML as a service. Is there any question?
Well, no, just a curiosity. Which physical devices were you using? They were specific from Ericsson, or
No. We've been using like Arduino, S32, Coral Dev Micro, a wide range of devices. There wasn't any Ericsson proprietary device, but actually this work I'm about to it was actually done already after my Ericsson tenure. I have like a very short demonstration here about the TinyML as a service front end. Basically, I won't spend the whole minute of the video, but here what you can see on the left-hand side is the whole pipeline process for managing the devices, adding the devices, and then also uploading the data set for training the devices. We are still in the device type, but it was like a very simple proof of concept of this. With all the different tabs, you can see here a subset of possible devices, selecting the appropriate data set for training the model, and then basically moving forward in, let's say, the machine learning pipeline, compiling the model, installing the model, and then actually running the actual inference itself. So this was just to show you the front end, and one of course like key aspect very briefly here was also respect the API, defining also appropriate API, probably one of the most important part of the work, and the possibility of relying on well-defined and set API for example, registering the device, etc., etc. So I just wanted to, this equivalent for the front end, but this from the back end and API point of view. So also in this case, I would like to briefly snapshot here a few references for this work. And Pietro, how much time you think we can continue still, just to understand?
I think we still have 10 minutes, more or less.
All right, perfect. So I would then like in short present in just one slide. Also in this case, you can refer them later on the slide. On the references I'm adding here, but this was the third item I wanted to present. I've been already mentioning about this hierarchical inference concept for seamless computing continuum, and the starting point, this was actually work initiated by India Networks, which was originally presented in one workshop organized a year ago, and the idea was to kind of add one additional player in this, let's say, extreme edge-to-edge computing interaction. Usually there is like a setup where it can be full offload, relying on TinyML on-device execution, as we have seen, offloading of the inference or partitioning the deep neural network between the end device and edge devices. And then the idea was to bring in this new concept of hierarchical inference. So we are actually still heavily working on this. And as I mentioned, this is work done in collaboration with edge network groups at India Network. And the idea is essentially to rely on these extremely constrained devices like Coral Dev Micro, not the dev board we have seen in the case of Edge, but kind of MCU powered devices, S32, trying to in front of, let's say, of the or let's say right after the execution of the tiny machine learning model that is fit on the device, trying to understand perform an additional classification and trying to understand whether the data sample that we are processing locally on the end device, IoT constrained devices, is simple or complex. And if the data sample is kind of tagged as a simple, then we will keep the execution of the AI inference on the TinyML device. On the contrary, if this is sort of tagged as a complex, will be offloaded to the edge. Here, obviously, we are relying on very lightweight classification algorithms right after, for example, object detection or this kind of algorithm in order to fit everything in the device. These obviously require also like increasing the capabilities of the base model, recalibrate the base deep learning model in order to kind of don't produce many false negative and false positive of this classification of the data. But as I mentioned, we start this work. We are actually continuing this work, and just to give you an example, we are now taking a broad range of devices, taking consideration those performance trade-off that we're mentioning earlier, was power consumption, but also connectivity. We're actually planning to hopefully like test this also in a LoRa network in order to have like a broad range of cases, scenarios in which we would be able to understand whether this hierarchical inference, when the approach can be useful and when is actually better to offload fully to the edge of the network. The reference I have not a specific slide, but for the work itself, but it's the one you can find here on the bottom right of this slide. And just to wrap up the last part of the presentation, I just would like very briefly to touch upon this, of course, big generative AI wave that, of course, has revolutionized the area of computer science, computing, etc. Not only, but the idea here would be also I start to think, obviously, whether there is any opportunity for edge and IoT. And for me, to be very honest, why this kind of area is interesting is because if back in the days we used to have a sort of problem for kind of quantifying the energy efficiency and the energy consumption, of the training of the model, traditional machine learning model, not necessarily a generative AI model, it actually turned out to be that with increasing usage of this type of services, the big problem is actually becoming the AI inference part. There are like interesting study about the cost of running AI inference, the imprint from the energy efficiency point of view is massive. So it's not only the training anymore that kind of affect and generate a massive amount of power consumption in data center. So I guess that here there is an opportunity, obviously, to think about whether bringing this sort of AI, new AI model into the edge or constrained edge could be an opportunity. And you might be familiar with one very recent event in the TinyML forum, which was a few weeks ago on generative AI on the edge. There were a lot of interesting contribution. You can take a look. And obviously, one big and here are some additional reference about the possibility that are already being envisioned for running a large language model specifically, or large vision models for also on edge devices. And obviously, like one big opportunity, along with the security and privacy aspect, another opportunity comes from the increasing availability of open source project. There is, of course, like a bunch of extremely complex and big large language models available, whether proprietary or open source. But there is also an increasing number of, let's say, tinier large language models that can possibly fit or start to fit in the sort of devices that we have seen throughout this presentation, edge and extreme edge. My perspective, like some of the very basic activity that we have been running, and this was one of the courses I've been running at the University of Helsinki, was actually to try to push the student on start to taking a look at the possibility of this model. We run this hackathon challenge where there was very simple scenario. The purpose was more like to trying to look at different model. We were using a different type of Raspberry Pi for and locally running a tiny small large language model. And trying to see what kind of very basic capabilities these models can have. There are a few models that can run basically out of the box in Raspberry Pi already, and also on something even more constrained. I'll get into that. And these are just an example, 3 examples that we have been using in this hackathon challenge. The scenario that the students had to model was very simple. The Raspberry Pi were kind of analyzing through language model some computing performance locally, CPU, memory, etc., and then generating a report and reporting it to central node. This was done like within a few hours. It was an hackathon, as I mentioned, and here just a very simple code snippet about the type of prompt. Of course, there is additional optimization. This is very basic activity, but it was a way also to try and understand, and I still can't really see what kind of possible and useful use case we could actually have in very constrained devices. This was, looking at the memory and CPU performance, and this was the generated output sent to the central node. Of course, not much verbosity, let's say. So nothing compared to what we can have obviously in cloud-based GPT models, but it's something that it was fun to try. One ongoing work is actually trying to build a sort of a benchmark suite for this kind of small language models in this type of devices. Whether it's Raspberry Pi or also something more constrained, there is nowadays the possibility for probably the only possibility of running this type of models on a microcontroller. Trying to build on benchmarking, trying to understand like when executing this type of application, where the and it's just a reference image, where the consumption of the resources is happening, what kind of optimization can possibly be done. It's very early stage, but the idea would be to try to look into this and try and possibly figure out a possible use case for this type of scenario. What I envision here, and I'm done, is perhaps the possibility of relying on this type of models on very constrained devices when looking at multimodality sources of data, so trying to take advantage of these capabilities of the models, if there is needed of matching some information where it's coming, whether from the peripherals or from the device itself, without need of building or relying on multiple models. And also possibly on the cooperation between devices, because this sort of specialization that we can give to the devices, we can perhaps build this sort of clustering and tailoring the cluster, and a similar kind of mechanism as we have seen in the first part of the presentation for handling these models also in the IoT and edge world. But I'm sure that there is really a lot of work that must be done, and obviously and a clear use case also to be found.
Yeah.
And that's pretty much about my presentation. Thank you so much.
Well, thanks a lot. Thanks a lot, everyone. Sorry, there is no much audience. Well, thanks a lot, Roberto. Very interesting, especially this last part. I was reading about this. I don't know. Sometimes I don't know. Sometimes when I read about it, I have the impression that we are trying to put, something, an elephant on a very small car. Because
Yes.
and as you said, there is find the actual case where you actually need an LLM on such a constrained device. It's hard for me to.
I agree. Yeah, that was the first thing I've been mentioning.
Yeah.
Indeed, that's why at the moment we are either trying to see the actual functionality out of the box, and then also trying to benchmark some of these from the qualitative and quantitative point of view. Some possibility could come from the for example, from this capability of code generation of the models, but already when it comes to very constrained, more limited models compared to the bigger one, this capability becomes weaker and weaker. So I think there is still a lot of work and near advancement that must be put in. But yeah, I think that it's an opportunity, but I wouldn't bet still everything on that.
No, I mean it's an interesting line to investigate to see what up to where we can get. But for me, it's it's complicated to find the real study case. Okay, this is the right situation where I need this type of model. No?
Yeah. Perhaps at the moment is mostly like engineering and development effort rather than a clear research path in that area. But I mean the field has been progressing so fast in the last year that we really don't know what to expect, and perhaps we will also have a chance to work on something useful there. But perhaps. If not on the very constrained when it comes to this sort of edge devices, still the possibility are perhaps a little bit higher there, especially when it comes to the cooperation of the devices when multiple of this language model, because of the requirements of the specific application, need to talk between each other. Perhaps there might be some opportunity. In the networking one, and this is a little bit beyond the IoT, but in networking, one big use case that could finally be enabled by this type of technologies could be intent-based networking, which has been around for many years. So yeah, let's see. We will see. I'm sure that
that's the fun part.
Yeah. Exactly.
Do some research and see if what we do can be useful.
Exactly.
Okay, so I think there are no more questions. Thanks a lot, Roberto.
Thanks to you. Thanks, Pedro.
Hope to meet you.
Thanks a lot again for the opportunity.
Let's stay in touch and work on.
Absolutely.
And for everyone that is attending and listening or will listen to this talk, thanks a lot. And see you in the following talk of this series. Thanks a lot. Bye-bye.
Thank you very much. Bye-bye. Thanks a lot.
Bye.
Bye.